In the end of our previous lecture, we were looking at the area of chemistry that we refer to as organic chemistry. And organic chemistry is chemistry based primarily on carbon-containing compounds. And within that group of organic chemistry, the simplest, I guess we would call it simplest from the standpoint that it contains only two elements, are the chemical compounds called hydrocarbons. By their name, hydrocarbons are compounds containing hydrogen and carbon only two elements in there. We looked at one group of those yesterday, which we called the saturated hydrocarbons, which have a general chemical formula relating to carbon and hydrogen of CnH2n plus 2. So whatever N is for carbon, for instance, if we had then a compound which had, say, 10 carbons here, so C10, that would tell us then that the number of hydrogens would be 2 times that, 20 plus 2. So the chemical formula for the organic compound would be, in that case, C10H22. We called this group the alkanes. As a family of organic compounds, we refer to them as the alkanes. And we looked at the first 10 of those alkanes yesterday and pointed out that some of these are fairly common compounds to us, things that we experience or utilize on a fairly common basis. The latter ones are those that are components of gasoline that we use in the automobile. The first one, the simplest of the alkanes, methane, we indicated was a component of natural gas. Propane and butane, of course, are two other fairly common alkane hydrocarbons. We also went on and talked a little bit about the fact that when you have the formula for a hydrocarbon, that it is possible that we can put these together it is possible that we can put these together in more than one way and actually produce then more than one chemical compound, meaning that the compound should have some different physical properties, melting points, boiling points, chemical reactivity, if they in fact are unique. And just to look at one here real quick, again, if for instance we had a compound C4H10, and that is an alkane hydrocarbon, meets the formula 2 times N plus 2 for the hydrogen. We could put the 4 carbons together like such and attach the 10 hydrogens, and as I indicated yesterday, the chemistry of carbon is such that it can have 4 bonds, 4 things attached to it. In our structural formula, we show those as dashes. We don't need to worry about what a chemical bond is at this point, but carbon can have 4 things essentially attached to it. Hydrogen can have only 1 bond. And so the only way we can hook hydrogens on there is we can't hook 2 hydrogens together and then have anything left to hook to the carbon. So if a hydrogen is hooked to a carbon, it is used up, then all of its ability to bond. Well, we could do it that way, or we could also hook 3 carbons like this, again with the hydrogens attached. And then the 4th carbon we could put here and attach hydrogens. And if we look, we should have again 4 carbons and 10 hydrogens surrounding it. And these are two different chemical compounds which we refer to then as isomers, structural isomers of the same chemical formula. Both of these are C4H10, both of these are alkanes, saturated hydrocarbons, but they are two distinct chemical compounds. And the naming rules used in organic chemistry are called the IUPAC rules, which is referred to in the text, but we're not going to spend any appreciable time as we go through the course worrying about applying IUPAC rules. We'll learn a few basic names of the organics and use them as such, but the IUPAC rule is to name the longest carbon chain as the basic name, and then to tell what other things might be present in the molecule. In this case, the longest continuous chain is 4. This compound is merely called butane. That's all we have to say. The ending, I didn't mention this in the previous lecture, but the ending of all alkanes is ANE. That's kind of a way we can get an idea when we see a name as to what type of chemical compound, what type of organic compound it is. This one has 3 carbons in a row. No matter which way you go, the longest continuous chain would be 3. And so the base name is propane. Again, notice it ends in ANE. But this time we have this little group hanging right here, and so we have to tell it it's there. In the detailed IUPAC system, we number the carbons and we tell what carbon the group is attached. So if we were to do that and call this carbon 1 and this one 2 and this one 3, we could then call this 2 to tell that on the second carbon of the propane there's something attached. And then we would say what's attached? Methyl. This is the name. Methyl is the name for this little CH3 group hanging on there, and we would call that then 2-methylpropane. And those are the same rules that we would use no matter how complicated the molecule might become. All right? So the main thing that we're looking at here, and the main thing that I want to stress, is the fact that we have so many different ways of putting together these carbon-hydrogen structures. As I mentioned yesterday, by the time we get to C10, C10H22 has about 70 different unique ways of hooking them together. 70 different names, 70 different compounds, all with the same chemical formula. So, chemical formulas tell us what and how much of each are there. Structural formulas tells us how they're hooked together. And if we have more than one way we can hook them together, those are referred to as isomers. Now, one other type of hydrocarbon that falls into this same general category are the cycloalkanes. Notice that we still have this name alkanes, but the cyclo part. The normal alkanes are chains, long chains. Things can be branched off of those chains, but as we see, they're just hooked together. But cycloalkanes now, by the term, would be cyclic, or in other words, we're going to hook things together. Let's take butane for a second. This is the way we would normally picture butane, 4 carbons in a row like this. If we were to take the 2 end carbons, this was 1 carbon and an end, and this was the other one. If we were to bend them around, we can actually hook them together like such, and we will still have hydrogens on here. So we end up with sort of a square-looking shape. Now, the naming for this is still that it's a butane because it has 4 carbons, and that would be the rule we would apply. But obviously this isn't the same butane as what we saw just a moment ago where the 4 were in a row. As a matter of fact, it doesn't have the same chemical formula, because here this has a chemical formula of C4H8. This is not an isomer of the previous chemical formula. Previous chemical formula was C4H10. This is a new compound, new chemical formula. But how are we going to show this now not being the same as the other butane? We use the prefix cyclo. So this would be called cyclobutane, which tells the reader that it's 4 carbons, but the N carbons are hooked back together to make it into a cyclic material. And the text shows a couple of cyclic compounds. One that is somewhat of interest, let's look at this one right here, which has 3 carbons on it, and each of these carbons would have a couple of hydrogens attached, like such. This is called cyclo, and the name for 3 carbons was propane, so cyclopropane. Cyclopropane is an anesthetic. It was used for many years in place of ether because of some of the ill effects that ether has, after effects, nausea, etc. And so ether was replaced for some time with a chemical called cyclopropane. The only problem is cyclopropane is very reactive, and so necessary precautions had to be taken. You couldn't have any static electricity. Things had to be properly electrically grounded. The clothing worn in for an operating room, you had to be careful that it wasn't clothing you wouldn't wear in a wool suit, which could pick up static electricity. So cyclopropane then was used as an anesthetic. Okay? Now, most of the hydrocarbons, of course, are obtained from our petroleum supply. And if you travel across Texas, Oklahoma, even parts of Missouri, Ohio, you may see in the fields along the road these pumps. These pumps that are moving up and down are pumping, literally physically pumping, then oil out of the ground. The oil or petroleum is a mixture. It's a mixture of all sorts of hydrocarbons, including all of those alkanes that we're talking about, except for methane and ethane, which are usually gases at room temperature, so they would have escaped as gases, but the rest of them will come out in this material called petroleum. Most of the wells drilled early on were what we would refer to as vertical drilling. In other words, they would put up a drill site, they would drill a hole straight down into the oil pocket or the suspected oil pocket, and then get the oil out. Now, the movies, of course, we often see they drill and they hit and the oil comes blowing out and sprays all over everybody, and there's a lot of celebration and that type of thing. That is true occasionally where we have oil underground that's under high pressure. But most of the oil underground doesn't come shooting out. It's not under high pressure. And so therefore, to get it out, we have to pump it out. It doesn't come spraying out. And so this is what we see as we travel across then this. Now, one of the problems with the vertical drilling process is the fact that you have to have one of those little drills, one of those little pumps, for every little puddle of oil that's down there. If you've ever driven around Los Angeles, for instance, there are places that these pumps are so close they're almost sitting on top of each other. They've drilled all of these little drill holes down into different pockets of oil to pump it out. Well, there are some new techniques being developed, and this is called horizontal drilling. And so this here is trying to demonstrate the difference between horizontal drilling and vertical drilling. As I say, most of the oil that we see today has still been drilled vertically. Because we're pumping out most of the big puddles, we now have to start looking at recovering our petroleum from the little puddles that are down there. And it's not economically feasible to drill down and tap into each of those little puddles, doing it vertically. But a technique has been designed, which we call horizontal drilling, where they actually go into an oil field and they drill, first of course vertically, but then they have the ability to begin turning the drilling bit so that mechanically it starts to curve, and now instead of drilling down, they're drilling horizontally through the oil field. Well, what this does is this allows them now to drill through many, many, many little puddles of oil instead of just going into one. So instead of putting an oil drill here and here and here, they put one over there and they drill and then go horizontally and pick up those other oil deposits. Okay? And in the process, of course, we can then economically recover some oil that previously we could not. And of course, if we can't recover the oil, we're going to have to depend more on exported oil. And if we do that, I mean imported oil, not exported, imported oil, which of course then puts our economy at the hands of other countries. And so we would rather have our own. This gives about a 90% increase in oil recovery, the horizontal versus the vertical. Economically, we can do it for about 10% of the cost, or recover about 90% more of the petroleum. Well, once the petroleum reaches the surface, of course, it's not very usable. If you've ever seen crude petroleum or crude oil, it's a nasty looking, syrupy, black material that doesn't seem to have any practical use. And so from that point then we have to process it. So here we're showing now the petroleum is coming into then a refinery, as we refer to it. We refine things, we separate things. The oil is coming in. The first thing we do is we heat it. All right, so we begin boiling it, we heat it to higher temperatures. Some of it turns to a gas state at that point. And we then begin pumping it into what is called a fractionating tower. Okay, a big column packed full of material, solid material, where this gaseous crude that we've now heated to high temperature begins moving through. The bottom is quite warm and it cools off as it goes toward the top. So only the most gaseous materials make it all the way through the fractionating column and are tapped off of the top. And we see here then, it shows up here that number 1, and this has a temperature of about 100 degrees, fraction number 1 comes off at the top. Fraction number 1 contains those things then that would be normally gases anyway: methane, ethane, and propane. So we then take those off. And then the second level there, the 100 to the 200 degree part of that fractionating column, we tap off another group of hydrocarbons which contain then the C4 through C12, which is primarily the automobile fuel. And so on down the line. The next is the diesels, the kerosenes. Finally, we get to materials that are liquids even at the higher temperatures, and those are our lubricating oils. And there are some things that we just can't do a whole lot with because they're really big hydrocarbons, and those are the tar and asphalt material that we end up with from the crude oil. Now, that particular process, as I said, is referred to as fractional distillation. Fractional because we're taking off fractions of portions of the compound as it goes through the column. Fractional distillation. If If you drive past a refinery, this is one of the major things that's going on there, is we're separating out into the various fractions. Now, different petroleum, different crude oils have different percentages of these. And of course, our demand for certain things are different. We have a very high demand in this part of the world for gasoline. And so obviously that's one fraction that we need a lot of. But sometimes we're going to end up with a whole lot of kerosene, diesel fuel, and lubricating oils on hand because we're producing and taking the gas fraction off very rapidly and using it. Well, then we have to look for some other processing methods. And one that is used is called cracking. Cracking is a very important part of the petroleum industry. By the name, you might guess, cracking means to break molecules into smaller parts. What we're going to do is we're going to take some of this material that is less useful, like kerosene, for instance, and we're going to take some of that C10 and C14s, and we're going to add a chemical, a cracking agent, and mix it with that and break it into smaller units of, say, C8s and C6s so that they can be used now as gasoline. So we can improve the productivity of certain of these fractions by using a chemical cracking process. Okay? Well, the petroleum industry and all of the other organic compounds that are associated with it is probably the major single one chemical industry in the United States. We depend a lot on petroleum and petroleum products, not only to drive our car, but all the plastics that we use are petroleum-based materials. That all comes from chemicals that we take out of petroleum and then chemically treat them to form polymers, to form plastics, etc. Most of the rubber we use is not natural rubber, it's synthetic rubber. Again, it's a petroleum-based product. So this is the starting point of some of the major industries in the United States, in the world for that matter. All right, well that wraps up what I have to say as far as Chapter 2, but I thought that it might be just a good idea, just sort of as a wrap-up of the math part of it, to look at one last problem from Chapter 2. And then we'll go on and talk a little bit about Chapter 3 this morning. Problem number 22 says, how much, or what is the mass of 8.46 times 10 to the 21 molecules of the chemical compound CH3OH? That particular chemical compound is known as methanol, also called methyl alcohol, also has a common name of wood alcohol. It's an organic compound. What we want to know is how much would this number of molecules of that weigh? Well, once again, just as a brief review, keeping in mind that we know that 1 mole of a compound is equal to its formula mass. So we have that relationship. And we know how to find now formula mass. To find formula mass, we take the atomic masses in their correct ratio and add them together. So in this particular case, the formula mass for wood alcohol, we have 1 carbon, so we have 1 times 12.01 for the carbon. We have 4 hydrogens, 4 times 1.01, and we have 1 oxygen, 1 times 16. And so we would have then a formula mass of 32.05 grams. So we know that 1 mole of wood alcohol weighs that amount. We also know that 1 mole of anything contains 6.023 times 10 to the 23rd units. In this particular case, the units, because we're talking about a compound, would be molecules. So we have two relationships, a relationship of molecules to moles. We have a relationship of moles to mass. And of course, using those two conversion factors, then we should be able to answer the problem. And I'll go ahead and do it on another transparency so I can work sideways so we can show both conversion factors. So the question was, now, how many grams of this CH3OH do we have in 8.46 times 10 to the 21 molecules? Now, the first relationship we're going to use then is the one that we see just above that, the relationship of molecules to moles. So we can say multiplied by 1 mole of CH3OH per 6.023 times 10 to the 23rd molecules. I'll just abbreviate it as M. And so molecules have canceled. And we're now at moles of CH3OH. And then we know that we can now bring in the relationship of mass. So multiplied by 32.05 grams of CH3OH per 1 mole of CH3OH, and moles cancel, and we're left then with grams, which is of course the unit that we were seeking. Once again then, we're ready to plug into our calculator and obtain the final numeric answer. And let's see, we would have 8.46 exponential 21, and again I stress, be sure not to hit the times 10 in there for those that may be using this for the first time in a course, divided by 6.023 exponential 23, then I'll hit the equal sign, and finally multiplied by 32.05. And my final answer is then that that number of molecules, which sounds like a whole lot, only weighs 0.541 grams. We would be limited to 3 significant figures based on this number here. This one would have 4, this one has 4, but that one has 3. So 0.45, I missed the spot there, 0. The actual number on the calculator is 4501793, and of course 3 places then would be 0. All right, any question on anything from Chapter 2? Chapter 3 now, we're going to go the next step. Chapter 1, we talked about the alphabet, the chemical alphabet, the symbols. Chapter 2, we talked about chemical formulas, put symbols together to make words. Chapter 3, we're going to put all of that together, symbols and then the words, the chemical formulas, to talk about chemical sentences dealing with chemical change, which we refer to as a chemical equation. Now, one of the characteristics of chemical change, as it is with also physical change, is that when something changes either chemically or physically, we do not create nor do we destroy any mass. In other words, whatever amount that we started with in a physical process and change it some way, we still have. For instance, if I take 10 grams of solid water, ice cube, and I melt it and I evaporate it, I still have 10 grams of water. It's in the gaseous state. It may occupy a whole lot more space, but we still have 10 grams of water. We don't lose any mass in a physical change. In a chemical reaction, we do not create and we do not destroy any mass. It may be hooked together differently, but whatever amount of chemicals we start with is equal to the amount of chemicals that we end up with. The law of conservation of mass then pertains to chemical change. To represent a chemical change, of course, we use what we call a chemical equation. And a chemical equation consists of two sides. The first, the chemicals we're starting with, which we call the reactants, and what we end up with, which we call the products. And what we're saying here then, in the law of conservation of mass, whatever mass of reactants we start with is going to be equal to the mass of products that we end up with. We're not going to lose any, we're not going to generate any, we're not going to produce any. Now, let's look at a particular chemical equation and see what kind of things a chemical equation can tell us. Now, one thing is that on this side, as I say, we have the reactants, and we have to have correct chemical formulas for each of the reactants involved. We must have correct chemical formulas for each of the products that is formed. We also, in some cases, if we know the information, we include the physical state for the reactants and the products. So what we're going to do here is we're going to put a little subscript S. Sodium is a metal, is a solid under normal conditions, and that's probably the way we would be using it in a chemical reaction. All right? So I put a little superscript S to represent solid. Water, normally we know, is a liquid, and so we put a little superscript L to give the physical state of water. Sodium hydroxide, that's the chemical name for this chemical compound over here, NaOH. This is actually going to be a solution. It's a water solution, and what we use is a AQ in parentheses, which stands for aqueous. Water is aqua, and so aqueous or water solution of the sodium hydroxide. And finally, over here we have hydrogen. Hydrogen, remember we talked about some of the gases, hydrogen, oxygen, fluorine, etc. Hydrogen is a gas at room temperature, and we put a little then subscript G. So we can include that kind of information. A little later in Chapter 3, we'll also include some information pertaining to energy. Whether energy is put in or energy is taken out of a reaction, we will show that as well. But for the time being, we'll limit ourselves to this right here. Now, let's see what the equation says to us, how we could read this equation. Well, one way we could, obviously, we could say that 2 sodium atoms, in other words, a chemical equation is an abbreviated form for putting down what we would say in normal words. We can say 2 sodium atoms react with 2 water molecules to produce 2 molecules of sodium hydroxide and 1 molecule of hydrogen. So what our chemical equation did was took that group of words then and put it into a shorthand fashion that we called the chemical equation. Now, we know that typically we don't deal in atoms and molecules. Our basic unit of measurement in chemistry, as we mentioned in Chapter 2, and we'll use throughout the course is what? The mole. And so we're going to say the same thing now, but this time we're going to put it in the units that we would normally talk about a reaction, which would be moles. And so we could then say 2 moles, and we can abbreviate it, 2 moles of Na, or sodium, react with 2 moles of water to produce then 2 moles of sodium hydroxide and 1 mole of hydrogen. So now we've expressed it in terms of moles rather than in terms of atoms and molecules, which of course is a more realistic way. But we also said at the beginning of this that a chemical reaction should show the law of conservation of mass. Or in other words, whatever I started with mass-wise on this side, we should end up with mass-wise on that side. Well, let's take a look once here. Then what we started with and what we ended up with mass-wise. On this side, we had 2 sodiums. So we have 2 times 22.99 grams, sodium's atomic mass, plus water. Okay, we have 2 waters up there, and water weighs, the hydrogen weighs 1.01 and oxygen weighs 16, so the water would weigh 18.02 grams, and there are 2 of them. That's why we're multiplying by 2 here for each. This should equal now 2 times the formula mass of sodium hydroxide, and let's see, we would have to calculate that. That would be 22.99 plus 1.01 for the hydrogen plus 16 for the oxygen. That'd be 24, which would be 40.00 grams plus the hydrogen, and there's only one of those, and it weighs 2.02 grams. Well, if we multiply this out, let's see, we would end up with 45.98 grams plus 36.04 grams equals 80 grams plus 2.02 grams, and we add this together, we see that we have 82.02 grams is equal to 82.02 grams. The fact is that, yes, mass has been conserved. We have shown that we have the same amount of product formed in a mass standpoint as we had then reactants to start with. Now, keep in mind that in a chemical reaction that atoms have a specific mass. And if atoms have a specific mass, then it would seem logical that if, in fact, mass is conserved in a chemical reaction, then atoms must also be conserved in a chemical reaction. And so we have an additional law here, which is the law of conservation of atoms. Now, an interesting chemical reaction that is indicated in the text is one that I mentioned the other day. Here is the element sodium. Sodium is a metal. It's a soft metal. Looks like a block of butter here. You can cut it with a butter knife, actually. It's that soft. It's a shiny, soft metal. And we have chlorine gas here, and chlorine gas is a yellowish looking gas, yellowish green gas. And as I mentioned before, both of these are very toxic to us. But if we put the two together, we get a spectacular chemical reaction with the release of a lot of heat and light and sparking and that occurring, and we end up with a product of sodium chloride, which, as I indicated, is essential for our diet. So a chemical reaction, this particular chemical reaction really does emphasize what happens in a chemical change. We have a major change in the properties of the matter involved, unlike we do in a physical change. Now, if in fact atoms are going to be then conserved in a chemical reaction, then we can carry out a process which we call balancing the chemical equation. We started in the previous one, the equation was all balanced. We had 2 moles of sodium plus 2 moles of water to get 2 moles of sodium hydroxide and 1 mole of hydrogen. That equation was already balanced. But if we start with reactants and put them together and make products and know what they are, to write the chemical equation, we have to balance it. We have to balance the atoms. And so let's take a look at how we go about the process. Anyone here that happens to be an accounting major, this should be right up your alley, because all we're doing is a bookkeeping process. How many atoms do we have in? How many do we get out? And we have to make sure that they balance. So the first one here, there are some rules in Chapter 3, early in Chapter 3, that indicate the order that one should balance the elements in the equation. And these are found on page 81. We start, first of all, with atoms other than oxygen or hydrogen. And we usually start with the elements furthest to the left in the periodic chart if we have some choice, like those that we call the metals. Then we go on to the other elements, and we finish by balancing hydrogen and then oxygen if we need to do so. I think what I'm going to do is I'm going to skip this one a second. This is problem number 2A at the end of the chapter. I'm going to go ahead and do 2C first. We have carbon, hydrogen, and oxygen to balance. And we have to have the same number of atoms of those over on this side as we have on this side. So the first element that we're going to look to balance then is the carbon, because it's not one of the hydrogen or oxygens, which we're going to keep to the end. So we look on this side and we say, all right, how many atoms of carbon do we have on the reactant side? 3, right? The chemical formula says C3, tells us we have 3 carbon atoms. Now we have to have 3 carbon atoms on the right-hand side then, on the product side. We see we only have 1. So somehow we have to get 3 over here. All right? Now, what we're going to do then is we're going to put a coefficient 3 in front of the carbon dioxide, in front of the CO2. You cannot balance by changing subscripts. Those subscripts are the chemical formula of the substance. If you change a subscript, you're making it a different chemical, and that's not what you're asking for. We now have the carbons balanced. Now we turn to the hydrogens. All right? And so we see that we have 6 hydrogens on this side, and we're only showing 2 over here. What would be the least common number for 6 and 2? Well, the least common number would be 6, and so we already have the 6 would go into 6 once, but 2 would go into 6 3 times, okay? So what you were saying was right. We need to multiply this one by 3 so that we have 6 hydrogens on each side. All right, so far we have everything balanced that way. Now we take a look at the oxygens. All right, over here we have 2 oxygens. Over on this side, we have 3 times 2, so we have 6 oxygens here. And then we have 3 times 1, so we have 3 more oxygens here. So we have a total of 9 oxygen atoms on this side. Now we must have 9 oxygen atoms on the other side as well. Well, how are we going to get 9 oxygen atoms on this side over here? Well, each oxygen molecule contains how many oxygen atoms? 2. So if we were to take 9 halves, or in other words, if we took 4½ oxygen molecules, we can take fractional molecules. We cannot take fractional atoms. But seeing that oxygen has 2 atoms per molecule, I can cut it in half, and I can take 1 oxygen atom. All right? Remember, all we're doing is showing a balance in terms of atoms. So we could say 9 halves oxygen molecules, and at this point we have a balance for the carbon, we have a balance for the hydrogen, we have a balance for the oxygens. However, the rule that we're going to use is we do not include fractions in balanced chemical equations. So I want to get rid of this fraction. Remember, it is now balanced. But I can do anything to that equation I want as long as I were to do it to everything in there. It wouldn't change the balance. So if I want to get rid of this 2, if I want to get rid of that half out of here, what could I do? I could multiply this whole thing through by 2. So if I do that, my final balance is going to look like this. 2 CH3H6s plus 9 O2 yields 6 CO2s plus 6 H2Os. So normally we say that a balanced chemical equation should show the smallest whole number balance that we can have. We should not include fractions in the balanced equation. Well, I think we're going to go ahead and wrap this up today, and we will continue on with some more balancing on their next lecture, and we will continue on in our discussion of Chapter 3.